Okay, so I'll start by reviewing some of the things we did last time, just so you can page in where we were and remember what I'm talking about. So last time we talked about the solvability of the consensus problem as a topological property of the protocol complex, namely that it's path connected. And then we applied the result to wait-free read-write memory. And so next we'll do the same for case set agreement. So this is what we were doing. And the key idea is that this notion of path agreement, or excuse me, of being path connected, can be thought of as taking a zero-dimensional sphere and putting it in the complex, and then filling it into a one-dimensional disk. And this is what it means to be path connected from a topological point of view. So we'll call such a complex zero connected, or connected in dimension 0. And we can generalize this to higher dimensional spheres. So we can say I can take a one sphere, a loop of string, and if any continuous map of that into the complex can be extended to a map of the two-dimensional disk, then we'll call that one connected. And of course, here's an example of something that's not one connected, because it has a hole, and there's no way you can fill in the interior of this map, because this hole here is a kind of an obstruction. 2 dimensions, we have a hollow sphere mapped into a space. We can fill it into a solid ball, and so on. So what we say is that a complex is n-connected if for every value less than or equal to n, every map of the n-dimensional sphere can be extended to a continuous map of the next higher disk. So intuitively, there's no hole there because you can fill it in. And we'll say that -1 connected is non-empty. That's a convenient border case. So the condition that we want for case set agreement is that if every n-simplex, the protocol complex reachable from that is k-1 connected. That is a set of executions where there's no failures. All the processes participate. And every n-1 dimensional sphere, that is all but one participate, that is one crashes, that's k-2 connected. And then we go all the way down the bottom and say if k of them fail, then we're -1 connected, meaning that we can tolerate the k failures. There's a non-empty set of executions. If this is true, then we can't solve case set agreement. And this is the basic property that it cuts across all the models that says when you can't do this case set agreement problem.
Can you go back to this line?
Mm-hmm.
So just to understand the notions better, why the first property doesn't imply the second? So there's no monotonicity here?
Well, imagine that. Imagine this protocol sits there and it waits for it all, and waits for all the processes to show up before it takes the next step. So in that case, this might be k-1 connected, but this would be empty, because because in this protocol, if one process fails, then nobody finishes. So really, what we're saying here is you tolerate k failures, and each execution where some number fail, you still have the appropriate level of connectivity. But implicit in this definition is the idea that you can have k failures, because if you have fewer failures, then this condition won't hold. So behind, there's an operational interpretation behind these topological conditions.
Can we say that there is a graph where each node is connected to k plus 1 other nodes? So if k nodes fail, so it will have a connection to that graph.
Well, these aren't graphs. These are simplicial complexes. So instead of thinking about edges between every pair, think of, say, a solid triangle among all three. And so, but it's not the case that it becomes disconnected if you remove a certain number. For path connectivity, you could partition it by removing a certain number. But that isn't what's going on here. What's going on here is we're really saying that there's no holes in certain dimensions when we look at all the possible sets of executions. So far, in order to do this, I need to introduce a little bit more machinery. So far, all the definitions we've given you are combinatorial.
Could you, just in order to get this slightly. So the simplexes at the beginning are input simplexes.
Yeah. If nothing happens, then an execution where nothing happens is just your input complex.
I mean, the n simplexes are input simplexes.
Yeah.
You say that, and the protocol maps them
into something more complicated. Yeah. All of the possible views of executions.
So really, n minus d simplex. The P of means the set of all executions with n minus d.
Participate.
I'm looking at an intermediate one.
Sure.
Say n minus 1 simplex. So you're looking at all the runs in which n minus 1 participate.
Exactly. Yeah.
And that needs to be, okay.
Yeah.
So that's the...
Yeah. So here we're saying if everybody participates, if the number of failures are 0, then you're k minus 1 connected. Then the protocol complex of all possible runs on all possible inputs. Sorry.
That higher ones are connected, and in the middle it's not connected, and the bottom is
Yeah.
connected.
Yeah.
By protocol being based on number of...
Yeah, you can have protocol complexes where it's connected in higher dimensions but not connected in lower dimensions, and we want to rule that out. It's easy to write that because if you just...
Well, one was what you told Hagit, but you could also have them connected at the bottom, at the top and the bottom,
Yeah.
in the middle. And
Yeah.
Okay.
Yeah. So what we're saying here is that you start here, you get a certain level of connectivity, and as you get failures, the level of connectivity sort of degrades in a graceful way. But it doesn't have to. You could certainly devise protocols where that's not true. But any protocol where this is true, then case-set agreement is impossible. So what I'm going to do now is I'm going to move from a purely combinatorial world into talking about Euclidean space and point sets and things like that. Now, I've been cheating because I've been drawing pictures of complexes and simplexes as if they lived in Euclidean space. And this is the way you've probably been thinking about them, but I haven't really defined what that means. And so now I'm going to do that. So a simplex is just a set of vertices, so it's just a set. Complex is a set of sets. And that's all that we've really needed so far to prove our results. But from now on, we'll talk about a geometric vertex as being a point in some sufficiently high-dimensional Euclidean space. Geometric simplex is the convex hull of some number of points in general position. And confusingly, the dimension of a simplex is 1 less than the number of its vertexes. So this is 0 dimensions, this is 1 dimension, and so on. And a complex is every pair of geometric simplexes intersects either in a common face or not at all. And that's the rule for embedding these things into Euclidean space. Any combinatorial complex can be embedded into a Euclidean space of sufficiently high dimension. So that's not really a problem. Okay, and we talked about the polyhedron. We want to distinguish between the point set that a complex occupies and its combinatorial structure. We'll use the absolute value sign to be the polyhedron, and this to be the combinatorial thing. And often we'll be kind of casual about this distinction. I'm not going to be pedantic about it. Yeah?
Does there have to be at least one intersection for a complex?
So complexes are closed under inclusion. So if a simplex is in a complex, all of its proper faces are in. So those intersections have to be there. But you could have a complex that consists of 2 isolated simplexes that aren't connected to each other and have no intersection with one another, and that's okay. So, I'm going to be, later on in the session, I'm going to be casual about the distinction between the geometric and combinatorial, because you can always go back and forth. But here, because I'm introducing the idea, I'm going to be a little bit pickier. So key idea that, what we really want, and the real reason I'm introducing geometry at all, is because we want to use the notion of a subdivision, where we take a complex. Here, this is a simple complex consisting of 2 triangles, their common edge, and the vertices, and so on. And now I'm going to chop it up into smaller complexes. And the idea here is that the polyhedron is the same, but the combinatorial structure is different. It's more complicated. So what does it mean for complex B to be a subdivision of A? Well, the first thing is that for each simplex of B, There's a simplex of A where the point set occupied by B is contained in the point set occupied by A. So the blue triangle here, alpha, is a simplex of the original complex. The small green beta is a simplex of the subdivision, and beta is contained in alpha in terms as point sets. So this is a geometric notion rather than a topological notion. The other thing is that for each big simplex, we can basically fill it up. It's the union of a bunch of simplexes of the subdivision. So here we've taken the blue alpha and we've chopped it up completely. Its point set is completely covered by the green simplexes. And those two definitions are what it means to be a subdivision. And again, you can't really, as far as I know, you can't really define this in a purely combinatorial way. You have to talk about point sets and Euclidean spaces. One particular subdivision that will come up all the time is called barycentric subdivision. So geometrically, it looks like this. We don't particularly care exactly where these points are, but it's usually we draw them in the barycenters. It has a combinatorial definition. Now, proving that this is a subdivision requires a geometry, but you can define it as in a purely combinatorial way. So the idea here is that each vertex of the barycentric subdivision is a face of the original simplex. So vertices of the subdivision will be faces of sigma. So here, for example, this vertex is just the green vertex of the big triangle. So the corner vertices represent themselves. This vertex here represents the edge, the red-green edge of the big triangle. And geometrically, we represent that by putting that at the barycenter of the edge it represents. And then the one in the middle represents the entire simplex. So we can go back and forth between this purely combinatorial definition, which we'll use for most of our proofs, and this picture, which we use when in our minds when devising the proofs. So a simplex of the subdivision is just a set of faces ordered by inclusion. So any chain of faces that are ordered by inclusion defines a simplex of the subdivision. So here, this is contained in this is contained in this, and when we put them all together, we get a simplex of the subdivision. When we want to talk about points in the interior of a polyhedron, we'll use barycentric coordinates. So that is, we'll find what's called the carrier, which is the smallest simplex that contains the point we want. And then we can represent that as barycentric coordinates in terms of the vertices of the carrier. So the three coefficients, T0, T1, T2 here, sum up to 1. And, and they're all between 0 and 1. And of course, in higher dimensional or lower dimensional, you'd have more or fewer coordinates. So we have the natural thing to talk about when you're talking about maps between combinatorial complexes is a simplicial map, which is just a map that carries vertexes to vertexes that also carries simplexes to simplexes. And when we're talking about point sets, the natural thing to talk about are continuous maps. And we're going to be opportunistic in moving back and forth between combinatorial and continuous things. Some results will be easier to prove in one domain and others in another domain. So we would like to go back and forth between simplicial and continuous maps when it's convenient to do so. So one direction is easy. So if we have a simplicial map, we can turn it into a continuous map by just extending over the barycentric coordinates. So I take the image of each vertex, and then I can add barycentric coordinates to, say, given a simplicial map, I can turn it into a continuous map that in some sense agrees with the simplicial map. So the other way is a little bit more complicated. Here we need something called the simplicial approximation theorem, which says that if I'm given a continuous map here, I can approximate it with a simplicial map. Unfortunately, it won't be a simplicial map between these two complexes. It'll be between a subdivision of this complex and the other one. So let me explain how that works. So I'm given a simplicial map between complex A and B and a continuous map. So here is the simplicial map that carries a vertex to a vertex. Now, suppose we also have a continuous map, F, that just maps points to points, that happens to take the point corresponding to this vertex and map it onto some point here, which is typically not a vertex. No, this map, the simplicial map does, but the continuous map doesn't. The continuous map just maps points to points. And so what I want to do is I want to construct a simplicial map that is close, arbitrarily close to the continuous map. And the next question is, well, what does it mean to talk about arbitrarily close? Well, we need a kind of a notion of a neighborhood. So given a vertex, the star of the vertex is the collection of simplexes that contain it. So here we have phi of v. We have v over here, phi of v over here. And we look at the star, which you can think of as kind of the combinatorial neighborhood of that point. So we've drawn that here in light blue. So we'll clean that up a little bit. And when we talk about the continuous map, we'll take the vertex back here and we'll look at its star here, which you can think of as the neighborhood of the source. And so we'll clean that up here. And the condition that we want is we want the image of the star of V under the continuous map to lie inside the star of the image of V under the simplicial map. So here we have, this is the, V is in the middle here, and this is its star. The
star V is f minus 1 of phi of V?
The star of V is the set of simplexes that contain V over here. So it is defined independently of any of the functions. And it's, the interior of this is an open set, so it has, some nice properties. And so we look at the image of star of V over here, which is not necessarily an open set. And then we want this to lie inside the star of the image under the simplicial map. And this is what our notion of two maps being close is, if it has this star property.
Is a continuous function from Rn to Rm?
Yeah, which happens to carry this, the polyhedron of this complex to the polyhedron of that complex. Yeah. I mean, most of the maps we'll have will be both into and onto, but it has to be into. So this is so we say that phi is a simplicial approximation of f if the the image of the star is inside the star of the image. Big one? Yeah. That's right. Who's keeping track of the bugs in the slides? Okay, mention that we should say for every vertex on this one. Okay, so simplicial approximation theorem says if I'm given a continuous function, there isn't necessarily a simplicial approximation from A to B, but we can take A and we can apply barycentric subdivision enough times and find a simplicial approximation to that. And I'm not going to prove that here because you can find it in any textbook. But this is going to be a very useful tool when we have a continuous map and we want to go over to a simplicial map. And in fact, it doesn't have to be barycentric subdivision. Almost any subdivision that shrinks the diameter of the simplexes will work. So this is the notion of barycentric subdivision, which will come in useful. So remember, we defined barycentric subdivision to say each vertex of the barycenter is a face of the simplex. The simplexes are faces ordered by inclusion. So I'm going to build a gadget out of this that will be useful for proving our lower bounds on K-set agreement, which is I'm going to take a scissors and start cutting off corners of the barycentric subdivision. So what I'm going to do is I'm going to take all the faces here. I'm going to take all the faces here that are of too small a dimension. In this example, it's going to be dimension 0. And I'm going to throw them out. And I'm going to look at the barycentric subdivision of what's left. And call that a truncated barycentric subdivision. And then once I do that, I'm going to subdivide it some more. in an arbitrary way. And then I'm going to color each vertex with a color from its carrier. So here, for example, this vertex, its carrier, which we've chopped away but is still sort of there, is either red or yellow. So we have a choice. We can color this either red or yellow, so I'm coloring it red. Here I'm coloring it green because it is a green corner. In the interior, I have a choice of all three colors. So this is just a Sperner coloring restricted to the a truncated subdivision. Okay, and so I claim here that some k-simplex here has k+1 distinct colors. So this is just a slight variation of Sperner's lemma that we used earlier. And the way to see this is go back to the faces that we've chopped off. We can draw edges or faces in higher dimensions between sort of the missing vertexes and the ones in the middle. And then it's not too hard to see that that's a Sperner coloring. So once we restore these things and we put in these kind of cones over the faces, there's got to be some simplex here that has n+1 colors. So every vertex here has a distinct color. And then we go back and we throw away the small ones again. And what we're left over with is a k-face, k-dimensional face with k+1 vertices. And it has k+1 distinct colors. So we have the coloring that we're looking for. And we're going to use this to prove the impossibility of k-set agreement the same way we use Sperner's in the original case. Okay, so here is how we're going to prove our theorem. I'm going to go from the kth truncated barycentric subdivision. I'm going to build a continuous map from the vertex from here to the polyhedron for the protocol complex that has the property that the image of each simplex is inside the protocol complex for that simplex. You know, so that this kind of approximates the protocol itself in some way. I'll remind you, this is the truncated subdivision. We're going to do this inductively over skeletons. So given a simplicial complex here, the skeleton of a particular dimension is simply all the faces of that dimension and lower. So the one-dimensional skeleton is just you look at all the one simplexes and zero simplexes. The zero-dimensional skeleton is just a set of vertices and so on. And this is good for inductive structure because we can define things on a skeleton and then sort of move into higher dimensions as by induction. So here what we're going to do is we're going to we're going to start out with a truncated barycentric subdivision. In this case, we started out with we have three processes, and we
since the skeleton is sort of the outside and the truncated subdivision is somewhat the inside.
Yeah, that's kind of the way we're going to do this. We're going to take this and we're going to map it. You know, before we could do this with Sperner's lemma because it was weight-free and we had and everything kind of coincided. Here, where things aren't necessarily weight-free, we've got to play different games with the dimensions. You know, everything I'm giving you here is a direct generalization of the Sperner's lemma proof that we did before, but with added we have to do arithmetic slightly differently. So here we have the truncated subdivision, and here we have the protocol complex, where the big thing is the protocol complex if all three participate. These are the subsets where only 2 out of the 3 participate. Oh, well, this is just a Venn diagram. So I don't know what the complex looks like. It's this big complicated thing. But I know that the set where only P and R participate is a subset of what happens when all 3 of them participate. Because one way Q, the MIT, can participate is by crashing right away. So I know that these things are included. I don't really know what their shape looks like. So. So these may intersect, but we don't know whether, for this argument, we don't care whether they intersect. In other ones, we will. So here we have this kind of Venn diagram, which may or may not be accurate in the corners here, and then we're going to build a map from here into there, over the skeletons. So in this case, n equals 2, meaning there are 3 processes, and we've thrown away everything below 1. So the base step, we'll start out with on the 0 skeleton here, which are just the vertices. And we'll say, well, we know that, so here, this vertex represents P and R running together. So we'll map it into a P of P and R, and we know this is non-empty because that's our hypothesis. Remember, our hypothesis said we are K-connected at the top, and then when we get down to K failures, we're non-empty. So we know that each of these things is non-empty, so we can just pick an arbitrary vertex in here and map an arbitrary vertex there. So the 0-dimensional case is pretty easy. Okay, so then inductively, so that's the base of the induction. On the 0 skeleton, everything is nice. So now I'm going to assume that we have this for the d-1 skeleton. And unfortunately, it's hard to draw this for interesting cases. So d is going to be 2. Actually, d is going to be 1 in the picture. So we have it for the 0 skeleton. Now I'm going to show you how to do it for the 1 skeleton. But think, d-1 and d. So we know that the image of each of these simplexes here is deconnected. Right, so we can fill in each of these things here is, in this case, we're talking about being path connected. But at higher dimensions, here we're talking about higher levels of connectivity. So what we've done is we've mapped the boundary of each of these simplexes into the space, but the boundary is just a sphere. And so because by hypothesis these things are connected, we can fill in this by a path in this case. And this is a continuous path. In higher dimensions, for example, we would send the boundary of a triangle in and we would fill it into a disk. But this map here is still continuous. So then so we inductively do this all the way. So now we have a nice continuous map that carries the all the way up to the K skeleton, because that's as far as the truncated subdivision goes. And then now what we do is we'll take a simplicial approximation. So we go from the continuous map to a simplicial map by taking a simplicial approximation. And so that requires subdividing this. So we had a continuous map from the truncated barycentric, and now we have some arbitrary subdivision. And we don't actually know what the subdivision looks like, but we know it is a subdivision. And we have a simplicial map that carries each vertex of the subdivision over here. And each edge over here of the subdivision maps onto an edge and so on. So now we have a simplicial map. Now the next step is to say, well, every vertex here represents the view of some process when it finishes our protocol. And it picks somebody's value because it's a K-state agreement protocol. So let's color this with the value of the winner. So we don't know who executed this vertex here, but they decided that that the orange process's input was that it would choose that value. So these colors here represent the colors of the winners. Now it's not too hard to see that, for example, this vertex maps over here where P and R are the only processes executing. So the only inputs you see are P's input and R's input, so the color you choose has to be either P or R. So continuing this way, we can see that the coloring that this inherits here from the decision values over here is a Sperner coloring on the truncated subdivision. And by that form of the Sperner coloring I proved, theorem that I proved earlier, we know that there's some simplex that has K+1 edges, K+1 distinct colors. But that corresponds to an edge over here that is K+1 distinct colors, which means there's some execution of the protocol where K+1 processes won in the sense that somebody decided their values. But the meaning of K-state agreement is you can't only pick a K or fewer. So that's the impossibility result there. Yes?
How do you even know that the final complex of P and R, for example, is contained in the final complex of PQR? For example, if it was a synchronous protocol, then after one round, he would know if Q doesn't participate.
But that's okay because we don't know whether this is synchronous or asynchronous. This is all the executions where P, Q, and R participate somehow, and they might participate either by crashing at the beginning. So not participating at all is also one way to participate in a Zen kind of way. But this is all the executions where P, Q, and R start out, and maybe what they do is one of them crashes before it takes a step. Maybe it keeps on running. But we know that these things, by the definition, these things are included because executions in which only P and R participate is also one where P, Q, and R participates. It's just that Q doesn't take steps. So the definitions guarantee that we have these inclusions here.
And the picture basically proved the classical consensus, one-set consensus.
Yeah. The one-set consensus, yeah.
You can do otherwise, but that's what this picture shows.
Yeah. Just because it's too hard to draw higher dimensions. But the combinatorial argument applies to arbitrary dimensions. Yeah, so don't confuse the proofs with the pictures. So the pictures are all in low dimensions because that's all I can draw. But and unfortunately, when you're talking about something like this, you lose some dimensions on the bottom and you're being squeezed up to the top. And you could probably draw this in 3 dimensions, but then be kind of confusing. Okay, so again, the idea here is that this proof didn't mention anything about the model. The only thing we talk about is the connectivity of the protocol complex. So as long as you can model your computations as a simplicial complex, and as long as they have this topological property of being connected in the way that I described, then it holds. So this holds for any of the variations as long as k failures are possible and as long as the connectivity properties hold. But a natural question, you might say, well, this is amazingly general, but does it actually apply to anything? And so and I think I said this last time. So we can get different flavors of results. If it's k-connected forever, then k-set agreement is impossible. If it's k-connected for our rounds, then we have a round-based lower bound. And if we have a model where we can talk about time, then we have a time-based lower bound. And in 2 topics for now, I'll talk about adversarial schedulers and how you can do all of these things in different models. For now, we're going to stick with the wait-free read-write memory. Okay, so what I'm going to do is I'm going to show that this works. This is true for read-write memory. That, in fact, we have a fairly strong property. I'm going to show you that for every input simplex sigma, the protocol complex for sigma is this connected. Is connected according to the dimension of sigma, which is enough to show that you can't do any kind of set agreement at all. Big pardon?
The thing you showed before, the manifolds.
No, because I didn't tell you that. I said the hypothesis is that you have this connectivity property, and if that's true, then k-set agreement is impossible. But I haven't told you we don't know yet whether read-write memory has this connectivity property or not.
But you showed the proof about manifolds.
I showed you a picture of a proof, but I didn't actually prove it. So it's true that the immediate snapshot is a subdivided simplex, and that implies the connectivity result. So.
We didn't show connectivity, but we had another proof on manifolds.
We proved it was a manifold, but a manifold isn't necessarily connected. So, for example, a torus is a manifold, but it has a hole in it.
So there are 2 different proofs, one via manifolds,
Yeah.
one via connectivity.
Yeah. So
The question is not whether the proof for the manifolds proves connectivity. The question was, didn't we already see the first box through a different proof?
With the manifold, yeah. So.
Or did you lie to us and you didn't?
Well,
No, I mean,
No,
the first 2 lectures or
Yeah.
lecture include a proof that set agreement is impossible in the simple wait-free, let's say not even a read-write model, but immediate snapshot.
So I proved it was impossible in the immediate snapshot model. Now, it's true that the immediate snapshot model is equivalent to read-write, but we don't know that yet.
Okay.
So if
You did see this result for the immediate snapshot.
Yeah, yeah.
And in order to derive the impossibility, all we need is, I think, to show that you can get immediate snapshot from read-write.
Yeah, yeah.
And that's
Yeah,
not
but
as complicated as the other direction.
yeah, but the problem with that is that all you get from that is that immediate snapshot. This is actually going to be useful for other problems.
Yeah, yes, I
Yeah.
think
For
that's,
impossibility, we can not do that because we say the possibility for snapshot, which
no,
That's
that's
not
actually
good.
not enough. You need a, but
a snapshot is stronger than that.
yeah,
This is trivial. It's stronger.
yeah.
Yes, so if I were to show that the immediate
Well,
snapshot,
the discussion is not whether this is useful.
Yeah,
but,
yeah.
Have we seen something similar before or something related before? It's just, I think,
Yeah,
to sort
that's
out
what-
things.
yeah, so another path to showing impossibility of end-set agreement in read-write would be to show that the immediate snapshot is equivalent to read-write.
But do you need, I'll repeat Nova's question, do you need equivalence for that? Because for impossibility, it's enough to show that there's a subset of the executions where the problem is not solved.
Well, it's a little bit, it's not as obvious as you might think because we were talking about iterated immediate snapshot where you have a clean set of memory on each round. Whereas the more natural thing to say is, well, we can look at immediate snapshot where you reuse the memory and somebody early can see a late write by someone else. And it turns out those are equivalent too, but that's a highly non-trivial proof. There's also the question about, is immediate snapshot really a subdivision? And I think the answer is yes, and I believe somebody actually wrote a proof of it once. I don't think anybody's written a proof that the sort of general immediate snapshot without the iteration is a subdivision, although everyone believes it to be true. And the reason is that proving that something actually is a subdivision is pretty tedious. And I don't think nobody's been motivated to do that. It would make a good homework problem. Okay, so we seem to be frozen here. Oh, okay. Actually, what time is it?
It's 3:10.
So maybe this.
10 minutes,
Yeah. So why don't we do a 10-minute break? Yeah.
So did you say that it was tedious or hideous?
I guess that's a value judgment.
What did you say?
I said tedious.
Tedious.
I mean, it's not hideous. It's not. I don't think it's intellectually difficult. It's just you've got to do barycenter coordinates and show that everything is included in that, and you end up doing a lot of arithmetic. Okay, so 10-minute break.